Hi everyone, I am Santhi from Department of Mathematics and Statistics, Bhavan Vivekananda College. I am here with my lesson 31 from linear algebra on eigenvalues, eigenvectors and diagonalization. In this lesson, I am going to explain about diagonalizable matrix. Before defining a diagonalizable matrix, I just want to show some examples or some few properties about diagonal matrix. First, let us look at a few points about diagonal matrices, which we will use in diagonalization of matrices. So, I'll give the first example here. Consider a diagonal matrix. Consider a diagonal matrix D is equal to 2, 0, 0, 2. Then D square is equal to, what will be D square? You can observe 2, 0, 0, 2. If you multiply this 2, 0, 0, 2, you will get nothing but 4, 0, 0, 4, which is nothing but 2 square, 0, 0, 2 square. Similarly, if you try to find D cube, if you try to find D cube is equal to, D cube is nothing but D into D square, any side you can multiply, D square into D you can think, D square into D. So what is D square? You have 4, 0, 0, 4 into D is 2, 0, 0, 2, which is nothing but it is 8, 0, 0, 8. This is nothing but 2 cube 0, 0, 2 cube. So if you observe in this way and so on, we can just check that D power k will be then, it will be 2 power k 0, 0, 2 power k. So this way concept we will be using in the next problems, and this is, I can say this is for k greater than or equal to 1, not from 0, right? Now let us look at this example where we use the previous concept about the diagonal matrix. So here a square matrix A is given 7, 2, minus 4, 1, and P is equal to 1, 1, minus 1, minus 2, and D is a diagonal matrix given. And also given that A is equal to PDP inverse. A is equal to PDP inverse. This you have learnt in similar matrices definition. So we can say A and D are similar to each other. That later we will discuss. Then find a formula for A to the power k. Now how do we use that previous concept about the diagonal matrix in this? Let us look at that. Here you are given A is equal to PDP inverse. This is equation 1. And now let us first see what is P inverse. P inverse is equal to 1 by det P into adjoint of P. That is equal to 1 by, what is the det P formula? AD minus BC into adjoint P means it is D minus B minus C A. If matrix P is A, B, C, D, then this is the formula for P inverse. Now this is equal to P is equal to AD 1 into minus 2 minus 1 into minus 1 into D minus B, D minus B minus C, and then A. So this, if we evaluate, this will be equal to minus 2 and plus 1 will be minus 1 into, and this is minus 2 minus 1 1 1, which is 2 1 minus 1 minus 1. This is P inverse. Now consider A power k. To find this, I will take A square is equal to, what is A square? A into E. That is equal to PDP inverse into PDP inverse. Now I'll group these terms. I'll group these terms as PD into P inverse into P into dp inverse, which is equal to pd into pd into p inverse p is I. So let me write it properly. pd into P inverse P is I into D into P inverse. Now this will be equal to, now I will write it as P into PD into PD into DP inverse, which is equal to P into D square into P inverse. So what did you have now? Implies you have that A square is equal to P D square P inverse. Similar way, we can have A cube is equal to P into D cube into P inverse, and A power 4 is equal to P into D power 4 into P inverse, and so on. A power K is equal to P into D power K into P inverse. This is what you have to find. Required one to find. Now what is the use of this one? For this is for k greater than or equal to 1. Then if we have this, you can find a power 100, a power 1000, anything, because multiplying a 100 times 1000 times will be difficult. Instead that you can just say p into d power 100. We know for diagonal matrix how to write d square, d cube and so on, we learned in the previous concept. So you can using this, the calculation of a power k will be easy for any k greater than or equal to 1. Now let us do an example on the same second one. So here you are given the same A is equal to P D P inverse, and P is given as 1, 2, 2, 3, and D is given as 1, 0, 0, 3, and you are not given anything about A, then find A power 4. That's solution. This is the D, right? Solution, we have A is equal to PDP inverse, implies A power 4 will be P into D power 4 into P inverse. What is the reason? Since A power K is equal to P into D power K into P inverse for K greater than or equal to 1. So to find A power 4, we need to find this. So for this, let us find first P inverse. So P inverse is equal to 1 by det P into adjoint of P, which is equal to 1 by det P is 1 into 3 minus 2 into 2, 4 into adjoint of P will be 3 minus 2 minus 2, 1. So which will be equal to, this is minus 1, so it is minus 3, 2, 2, minus 1. This is P inverse. And what else we need? This is the thing we are going to find. So we need now even D power 4. D power 4 is equal to 1 power 4, 0, 0, 3 to the power 4. That is equal to 1, 0, 0, 3 to the power 4 will be 81. Therefore, A power 4 is equal to P into D power 4 into P inverse. We have P, that is 1, 2, 2, 3 into T power 4 is 1, 0, 0, 81 into P inverse is minus 3, 2, 2, minus 1. So you multiply from left to right, multiply first. Anyway, you can multiply. So these two, if you multiply, you will get 1 plus 0 and then 0 plus 162 and then 2 plus 0 and then 0 plus 243 into minus 3, 2, 2, minus 1. So again you multiply these two now. So it is minus 3 plus 324 and then 2 minus 162 and then minus 6 plus 486 and then next one is 4 minus 243, that is equal to 321 minus 160 and then 480 minus 240. This is a power 4. Without knowing a, we just found a power 4. Now let us look at another example. Use the factorization a is equal to PD P inverse to compute a power k for the matrix. So here it is understood that this is a is equal to PD P inverse, means this is a and then this is P and then this is D and this is P inverse. So let us take another color. Now what do you have to find? A power k we have to find. So solution, we have a power k is equal to P into D power k into P inverse. This is what we know. So now you have P, you have 1 0 2 1 and D is A0 0 B. What will be D power k? A power k 0 0 B power k into P inverse is 1 0 minus 2 1. Just multiply these two, which is equal to this is A power k plus 0 0 plus 0 and then 2 times A power k plus 0 and 0 plus B power k into 1 0 minus 2 1. Then again you multiply A power k and then plus 0 and then 0 plus 0 and then this is 2 into A power k minus 2 into, let me write again, it is 2 into A power k minus 2 into B power k and then 0 and then plus B power k. So this is equal to, implies I have A power k is nothing but A power k 0. I can take 2 common, A power k minus B power k and then B power k. After learning about a few concepts on diagonal matrices, now let us go to the main concept of this lesson, that is diagonalizable matrix. Now let us look at the definition of a diagonalizable matrix. A square matrix A is said to be diagonalizable if A is similar to a diagonal matrix D. Before we learned what are similar matrices, so you call a square matrix A to be diagonalizable if A is similar to a diagonal matrix D. That is, we can say, if there exists a diagonal matrix D and an invertible matrix P such that A is equal to PDP inverse. What do we mean by this PDP inverse? A is equal to PDP inverse. A and D are similar. Then A is diagonalizable. So we can say that any square matrix A is said to be diagonalizable if there exists a diagonal matrix D and there exists a matrix, invertible matrix P such that A is equal to PD P inverse. Now let us prove a theorem which is called as diagonalization theorem. It states that an n by n matrix A is diagonalizable if and only if A has n linearly independent eigenvectors. So this theorem gives us a shortcut to check the diagonalizability of a square matrix. So let us try to prove this theorem. Proof. So what is given to us here? A is let A be an n by n matrix. Now what is there in this theorem? A is diagonalizable if and only if A has n linearly independent vectors. That means what do we have to prove? To prove, two parts are there in this theorem. That is, the first one we have to take A is diagonalizable implies A has n Li eigenvectors. On the other hand, converse, and A has n Li eigenvectors, we have to consider this, implies A is diagonalizable. So there are two parts in this. First part is taking A diagonalizable, proving A has n Li vectors, and the second part is taking supposing that A has n Li eigenvectors and proving that A is diagonalizable. So let us first start with the first part. That is the first part. What is that? Let A be diagonalizable. Then by definition, there exists an invertible matrix, P, an invertible matrix P, and a diagonal matrix. This is a definition of diagonalizable matrix. Diagonal matrix D such that what do we have? A is equal to PD P inverse. So it is A is equal to, let me take A with this, A is equal to P dP inverse D into P inverse. So let me write this also. A is equal to, this is what? Definition of diagonalizable matrix. That implies this, I can write this as multiply both the sides with P, A into P is equal to, so you will have here, if you multiply this with P, D, and then P inverse into P, which is equal to P, D, and then P inverse P, that is equal to, we have P, D, this is what you have here. That implies you have the equation, you have AP, A into P is equal to P into D. A into P is equal to P into D. Let us take it as equation 1. Equation 1. Right. Now here what did we suppose P? P is an invertible matrix. Then, so let me take here, let P is equal to, I will take the matrix like this, V1, V2 and so on Vn. So what do we mean by here? That is, here I say this one as where V1, V2 and so on Vn are columns of P. So here V1 is not a single element, it is a vector which is a column in. Now let us suppose here, let us take let D is equal to, it is a diagonal matrix. What is a diagonal matrix? Only the principal diagonal elements are all non-principal diagonal elements are zeros. That is what we have to take. That is lambda 1, 0, and so on 0, and then 0, lambda 2, 0, 0, and so on. Here you can have many rows, and then here you have, this is 0, 0, and so on. Let me write this as lambda n. So this will be also, I will write so this is lambda 1, lambda 2, and so on, lambda, and this is a diagonal matrix. Now let us use this equation. What do you have? AP is equal to PD. So then for that I will write what is AP. Then A into P is equal to. So I have A into, I have V1, V2, and so on Vn. That I can write it as, it is equal to A into V1, A into V2, and so on A into Vn. Then what is a PD? And PD is equal to, what is P is again V1, V1, P is V1, V2, and so on Vn into, then what is D, diagonal matrix? You have, it is lambda 1, and then 0, and so on 0, and then 0, lambda 2, and so on 0, and then, and you have here, this is 0, 0, and so on, lambda n. Then what is the product? What will you get it as product? I can say, because if I, how do we multiply matrices? First row I'll take, that means first row elements in V1, V2, I'll multiply them with lambda 1, this first column. So I will get here nothing but I will get lambda 1 V1, lambda 2 V2, and so on, lambda n Vn. Now equation 1 implies, equation 1 implies we have AP is equal to PD. That implies we have AV1, AV2, and so on AVN is equal to lambda 1 V1, lambda 2 V2, and so on lambda n Vn. So if you compare the like terms, we'll get these equations implies we have AV1 is equal to lambda 1 V1, AV2 is equal to lambda 2 V2, and so on, and so on. AVN is equal to lambda n Vn, which implies, so what is this definition? Here I can say this is a definition for eigenvalue, eigenvector. If you observe here, that implies V1, V2, and so on Vn are eigenvectors of A, the matrix A, corresponding to the eigenvalues lambda 1, lambda 2, and so on lambda n of A. This is the, because we have what is the eigenvalue, eigenvector definition. Here you have Ax is equal to lambda x, implies x is eigenvector and lambda is eigenvalue. So this, if you apply the same, you will get this. So what do you mean by that? Now here, and but we have V1, V2 and so on Vn as columns of P. So what are these V1, V2 and so on Vn are columns of P, right? Then if they are columns of P, then what is P? And P is invertible, which implies det P not equal to 0. That implies columns of P are linearly independent. That implies V1, V2 and so on Vn, which are eigenvectors of V, A, eigenvectors of matrix A are linearly independent. Hence, we proved that A is diagonalizable, implies eigenvectors of A are linearly independent. Now let us prove the converse, second part of the theorem. Then second part of the theorem, that is to prove what is second part of theorem? A has n Li eigenvectors, implies you have to prove A is diagonalizable. So for this, let us suppose, let A be having n Li eigenvectors, that is, let V1, V2 and so on Vn be Li eigenvectors, linearly independent Li eigenvectors of A correspond. So if there are eigenvectors, there should be eigenvalues. So these eigenvectors corresponding to the eigenvalues. What are eigenvalues? Lambda 1, lambda 2 and so on, lambda n. N eigenvectors are there, n eigenvalues we are taken. Then by definition we have A V1 is equal to lambda 1 V1, A V2 is equal to lambda 2 V2 and so on. A Vn is equal to lambda n Vn. Then if we consider P is equal to V1, V2 and so on Vn, that is a matrix with eigenvectors as columns and D is equal to D is equal to lambda 1, 0, 0, 0, lambda 2, 0, and so on, 0, 0, and so on, lambda n. That is a diagonal matrix with eigenvalues as diagonal entries. Then we have AP is equal to PD. AP is equal to PD. Then we have this, let me give it equation 2. Right, since V1, V2 and so on Vn are linearly independent, we have det P is not equal to 0 because they are columns in matrix P, which implies P is invertible. That is, P inverse exists. Then 2 implies in equation 2, multiply both the sides with P inverse. AP into P inverse is equal to PD, not the other side, PD into P inverse. Let us multiply P inverse. Now which implies this is A into I is equal to PD P inverse. That implies A is equal to PD P inverse. A is equal to PD P inverse. What do we mean by this? A is equal to PD P inverse. This is the definition of diagonalizable matrix. That implies A is diagonalizable. That is what we proved here by taking vectors or eigenvectors are linearly independent. We proved that A is diagonalizable. So hence the theorem is proved. We have one more theorem. Its statement is an n by n matrix with n distinct eigenvalues is diagonalizable. That means suppose if you have a 3 by 3 matrix, then it will have maximum 3 eigenvalues. Suppose they are lambda 1, lambda 2, lambda 3. If these 3 eigenvalues are distinct, that means lambda 1 not equal to lambda 2 not equal to lambda 3, like 1, 2, 3, like that. Then that matrix will be diagonalizable. So let us prove this theorem. So you are given with the matrix, let A be an n by n matrix. Let lambda 1, lambda 2 and so on lambda n be the n distinct eigenvalues of A. Now, if they are n distinct, that is what we have to take with n distinct eigenvalues. If this matrix has n distinct eigenvalues, then it should have correspondingly n distinct eigenvectors. So implies there exist n distinct eigenvectors corresponding to the above eigenvalues. That is, let V1, V2 and so on Vn be the distinct eigenvalues for lambda 1, lambda 2 and so on lambda n respectively, corresponding ones lambda n respectively. That means V1 is the eigenvector of lambda 1, V2 is the eigenvector of lambda 2 and so on. Vn is the eigenvector of lambda n corresponding to lambda n. These are the eigenvectors. Then by a known theorem, we had a theorem, n distinct eigenvectors of n distinct eigenvalues are linearly independent. So by a known theorem, V1, V2 and so on Vn are linearly independent. That implies if they are linearly independent, that is by diagonalization theorem, the matrix A is diagonalizable. Because what does diagonalization theorem says? If A has a distinct linearly independent eigenvector, then it is diagonalizable. So A is diagonalizable. That is what the theorem. Next, let us look at the procedure to determine a matrix is diagonalizable or not. First point, consider the given square matrix A of order n. A matrix A is given. Then second point, find the characteristic equation of A, that is for non-triangular matrices. Why do we need this characteristic equation? Let us look at the next step. Find the eigenvalues of the given matrix. How do you find eigenvalues? After you get the characteristic equation for non-triangular matrices. Suppose it is a triangular matrix, you can directly say that the diagonal elements, principal diagonal elements are the eigenvalues. Our final aim is here to get the eigenvalues of the given matrix. Now, right, then if A has exactly n distinct eigenvalue, what do you mean by that? Suppose A is a 3 by 3 matrix, order is 3 by 3 and you got 3 distinct eigenvalues like 1, 3, 5 like that. Then their corresponding n distinct eigenvectors will be linearly independent. This is, we have done a theorem that distinct eigenvectors of distinct eigenvalues are linearly independent. Then, hence by diagonalization theorem is diagonalizable. Since the eigenvectors are linearly independent, by diagonalization theorem, the given matrix is diagonalizable. Otherwise, that is, suppose if A has some or all repeated eigenvalues, suppose A has 5 eigenvalues, among those 2 are repeated and 3 are distinct. Like suppose you have 2, 2, 3, 4, 5. So A has 5 eigenvalues, among those 2 is repeated twice and 5, 4, 5 are repeated one time. Then find their corresponding eigenvectors. So if the eigenvalues are not distinct, you have to find eigenvectors. After that, fifth point number 5. Consider these eigenvectors as columns of a matrix P. So take a matrix P and just write these eigenvectors as columns of P. The next point, if det P not equal to 0. So after taking like this matrix P, evaluate a determinant, then if det P not equal to 0, then the eigenvectors are linearly independent and hence A is diagonalizable. Otherwise, if det P is equal to 0, then you will simply say that A is not diagonalizable. So here note, a square matrix of order n can have a maximum n eigenvalues. Now we will do a problem to check whether a given matrix is diagonalizable or not. So what is the first step we have to use to determine a matrix is diagonalizable or not? We have to find first the characteristic equation or polynomial or equation for the matrix, and then we have to find its eigenvalues or characteristic values. So let us write CH polynomial. Characteristic polynomial of A is det A minus lambda I. Now let us find det A minus lambda I is equal to, how to find the determinant? It is 1 minus lambda 3 3, and then minus 3 minus 5 minus lambda minus 3 3 3 1 minus lambda. Just in the diagonal element, for the diagonal element subtract lambda. So expand its determinant by the, I am expanding by the first row. So you will have here 1 minus lambda into minus 5 minus lambda into 1 minus lambda, minus 5 minus lambda into 1 minus lambda, and then minus 3 into 3, and then minus 3 into, and then minus 3 into 1 minus lambda, minus of minus 3 into 3, plus 3 into minus 3 into 3, minus of minus 5 minus lambda into 3. This is what expanding the determinant by first row we are expanding. So this is equal to 1 minus lambda. Always first simplify, or first to some extent what is there in the bracket. Then you will get this one as minus 5 plus 5 lambda minus lambda plus lambda square plus 9, and then minus 3 into minus 3 plus 3 lambda, and then it is plus 9, and then plus 3 into minus 9 plus 15, and then plus 3 lambda. Let us simplify it and see. And this is 1 minus lambda into, what do I have here? Lambda square minus plus 4 lambda, and then plus 4, and then plus, not plus, this is minus, and this is 3 lambda plus 6, and then plus 3 into 3 lambda plus 6. Now you can see these two will get cancelled, and here also you have minus 3, so they will both will get cancelled, and then what will remain here, this is equal to 1 minus lambda into, and this is lambda plus 2 whole square. Then what is the characteristic equation? Therefore characteristic equation is det A minus lambda I is equal to 0, that is 1 minus lambda into lambda, 1 minus lambda into lambda plus 2 whole square is equal to 0, which implies lambda is equal to 1, or lambda is equal to minus 2 2 times. So therefore, what are the eigenvalues or characteristic values? Eigenvalues are 1 minus 2 minus 2. These are not distinct, because here you have these two are repeated. Then what do we mean by that? Therefore, what do we have to check? Therefore, we need to find characteristic vectors, or you call them as eigenvectors. So we learned how to find characteristic vectors or eigenvectors. First we will find for lambda is equal to 1. So first one, characteristic vector for lambda is equal to 1. So for this, we will consider the matrix A minus lambda I into X is equal to 0. Where what will be X here? It is a 3 by A is a 3 by 3 matrix, so you will have this one as X1, X2, X3. Right. Now A minus lambda I is equal to, so what is A? First let us write A. It is 1, 3, 3, minus 3, minus 5, minus 3, and 3, 3, 1. Then what do we mean by A minus lambda I? For the diagonal element, subtract lambda. What is lambda? 1. So minus 1 in the principal diagonal elements, subtract. Then you will be getting this matrix will be equal to 0, 3, 3, minus 3, minus 6, minus 3, and then 3, 3, 0. Then what do we mean by A minus lambda I into X? That will be equal to 0, 3, 3, minus 3, minus 6, minus 3, 3, 3, 0 into, what is X we have to take here? X1, X2, X3. That is what we have taken X as. X is equal to X1, X2, X3. Now to find this, X is equal to X1, X2, X3. For this, consider augmented matrix, because you need to solve the system of equations. Augmented matrix, what is that? A minus lambda I with 0. That is equal to A minus lambda I 0, 3, 3, and minus 3, minus 6, minus 3, 3, 3, 0 with 0, 0, 0. Now you have to reduce this to echelon form. Then you have here this first row, first element is 0. We don't want this. So let us first do the transformation. Interchange the rows. So we will change R1 to R3. Then this will be equal to 3, 3, 0, 0. And then minus 3, minus 6, minus 3, 0, 0, 3, 3, 0. Now you have here pivot position. Before taking the pivot positions, I want to do the step that for R1, R1 by 3, for R2, R2 by minus 3, for R3 also R3 by 3. Then what would be this matrix? This will be transformed to 1, 1, 0, 0, 1, 2, 1, 0, 0, 1, 1, 0. Then your task will be easy. This is pivot position, making this using this, make these zeros. This is pivot and this one. Let us look at that, what happens. So what is the transformation I apply here? The transformation I apply here for R2, R2 minus R1. Then the matrix is transformed to 1, 1, 0, 0, 1 minus 1, 0, 2 minus 1, 1, 1 minus 1, 0, 1, 0. And then even I don't want anything because here R3 it is the same. So it is 0 element already, first element. So this is this. Now again mark the pivot position, and here this is a pivot position. So what do you do now for R3? R3 minus R2. So this will be transformed to 1, 1, 0, 0, and then 0, 1, 1, 0, 0, 0, 0, 0. Now what are the pivot positions? Here you have So this one you have here the equations. R1 implies this. Let me finish this. R1 implies the row 1. Not this R1. Let us see. R1 implies I have x1 plus x2 is equal to 0. And then next one is R2 implies I have x2 plus x3 is equal to 0. Right. Now what can I write here? We can suppose that we have this is 1 and this is 2. So now let us keep it x2 as x2. Then x1 implies 1 implies x1 is minus x2. This is equation 3. And then 2 implies x3 is equal to minus x2. This is 4. Then x3 is x3. Therefore, what do we have? Therefore, we have x1 is minus x2. x2 is x2. And then x3 is equal to also minus x2. Therefore, eigenvector x is equal to x1, x2, x3 is equal to x1 is minus x2, x2 is x2, x3 is also minus x2. So this I can take, if I take x2 common, minus 1, 1, minus 1. This is the eigenvector. This is the eigenvector for lambda is equal to 1. Now similar way, let us look at the eigenvector for lambda is equal to 2. Then next one, eigenvector for lambda is equal to minus 2. So for this also consider a minus lambda I. Let me take into y is equal to 0. Here I will take y as y1, y2, y3. You can take even x1, x2, x3, but I am taking here y1, y2, y3. So for this consider what is now a minus lambda I for lambda is equal to minus 2. Yeah, this is equal to. So 1 minus lambda in the diagonal. If this is a, suppose a is equal to 1, 3, a is equal to 1, 3, 3, and then minus 3, minus 5, minus 3, and 3, 3, 1. Then in this, in diagonal elements, you have to subtract lambda. Minus of minus 2, minus of minus 2, and here also 1 minus of minus 2. So this is equal to 3, 3, 3, minus 3, minus 3, and then minus 3, 3, 3, 3. Now consider augmented matrix. Consider augmented matrix A minus lambda I and comma 0, that is equal to 3, 3, 3, minus 3, minus 3, minus 3, 3, 3, 3, 0, 0, 0. Then reduce it to echelon form just to do the transformation for R1, R1 by 3 for R2, R2 by minus 3, R2 by minus 3, and for R3, R3 by 3. Then this matrix will be reduced to 1, 1, 1, 0, minus 1, minus 1, minus 1, 0, 1, 1, 1, 0. So this is not a minus 1 because we have divided with minus 1. This will be 1, 1, 1 only. So this will be, now apply transformations. What is the transformation you will apply here? For, because this is pivot and these two R2, R2 minus R1, and for R3 also R3 minus R1. Then this matrix is reduced to 1, 1, 1, 0, 1 minus 1, 0, 1 minus 1, 0, 0, 1 minus 1 again 0, 1 minus 1, 0, 0, 0. So it has only one pivot column, pivot element. Now how to get these values? So this is multiplied with y is equal to, what did we take? y1, y2, y3. So first row implies, R1 implies, I have y1 plus y2 plus y3 is equal to 0. Right. What do you mean by that? y1 is equal to minus y2 minus y3. See here, there are no more equations. There are three variables, but you have only one equation. So it will have infinite solutions. How do you write that? Then y is equal to, y1 is minus y2 minus y3. Then y2 will be as it is y2. You can't get one more formula. Similarly, y3 also the same. Similarly, y3 also the same. So this is y2 and this is y3. This you can write it as y2 if you take common, minus 1, 1, 0 plus y3 into minus 1, 0, 1. Therefore, minus 1, 1, 0, comma, minus 1, 0, 1 are the eigenvectors for lambda is equal to minus 2. Now how many eigenvectors total you have? Therefore, A has 3 eigenvectors. What are those? First one is 1 minus 1 1, and then not 1 minus 1 1, it is, we have taken it as minus 1 1 minus 1, and then the second vectors just now we have written minus 1 1 0 and minus 1 0 1. Now what do you have to do? Next one is you have to write P. What is P? P is the matrix having these 3 eigenvectors as column. So consider P is equal to these 3 eigenvectors as columns, minus 1, minus 1, minus 1, 1, 0, and then minus 1, 0, 1. Now, what will be det P? Let us calculate determinant of P. Determinant of P will be minus 1 into 1, minus 1 into 1, 1 minus 0, then plus 1 into 1, and then minus 1 into 1, which is equal to minus 1 plus 1 minus 1, and these two will get cancelled. This is equal to minus 1 not equal to 0. That implies P is invertible, that is eigenvectors or Li implies A is diagonalizable. Look at this example. Determine whether the following matrix is diagonalizable. A is given a 3 by 3 matrix. Let us look at the solution. And how do we check whether it is diagonalizable or not? We have to find the characteristic equation and eigenvalues. Finding eigenvalues is important. But here you can observe this matrix to be an upper triangular matrix. So here A is an upper triangular matrix. If A is an upper triangular matrix, then what are the eigenvalues of A? Implies eigenvalues of A are 5, 0, minus 2 elements from the principal diagonal. That implies, so already we got eigenvalues, and which are even you can observe which are distinct. Implies their corresponding eigenvectors will be linearly independent. That implies if they are linearly independent, we have implies by diagonalization theorem A is diagonalizable. So here we have two practice problems. For these two matrices A and B, just determine whether they are diagonalizable or not. Let us look at a few more points now about diagonalizable matrix. First point is, if a matrix A of order n by n is diagonalizable, then its eigenvectors form a basis for Rn. So what do you mean by that? Suppose I have a matrix A, its order is 5. Suppose it is diagonalizable. Then how many eigenvectors it may have? If it is of order 5, it may have eigenvalues maximum 5. So suppose it has eigenvalues, this has eigenvalues 1, 2, 2 and 3 and then minus 1. So 5 eigenvalues, but among these 2 are repeated. So you can say distinct are only 4. This is lambda 1, lambda 2, lambda 3, lambda 4, lambda 5. Then these 5 eigenvalues will have, if it is diagonalizable, then all these will have eigenvectors x1, x2, x3, x4, x5. That means though 2 is repeated, this 2, in this case, because it is diagonalizable, it will have 2 different eigenvectors. 2 will have 2 eigenvectors. In some cases, though the value is repeated, you will have only one eigenvector. Right. So it doesn't need to be always. Since it is diagonalizable, it must have, since order is 5, it must have 5 eigenvectors. Okay, need not be 5 eigenvalues, but 5 eigenvectors. So if it has 5 eigenvectors, these 5 will be linearly independent, then only it will be diagonalizable. And these 5 will be forming, these x1, x2, x3, x4, x5 will form a basis for R5. All these will form a basis for R5. So that is what here the first point says, a matrix of order n by n, if it is diagonalizable, then its eigenvectors will form a basis for Rn. That implies you can even say a diagonalizable matrix A of order n by n must have n linearly independent eigenvectors. Now, let us come to the second point. If a matrix A is of order n by n, then not and the sum of the dimensions of the eigenspaces of the eigenvalues of A is equal to n, then A is diagonalizable. So let us just look at this sentence again. Order is n by n, matrix order, sum of the dimensions of the eigenspaces. So because each eigenvalue will have an eigenspace, then a number of vectors in the basis of eigenspace will give you dimension of the eigenspace. Then sum of all these dimensions must be equal to n, then A is diagonalizable. Let us look at it by these few lines. Here for example, I have taken order of A is equal to 5 the same way. Then eigenvalues are 1, 3, minus 1. So though it is 5, there are three eigenvalues. That means some eigenvalues must have been repeated. Then and it is like this, one has two eigenvectors, so it is repeated twice, you can understand. Then what is the dimension of E1? Then it is equal to 2. Then 3 has this eigenvalue, 3 has two eigenvectors, dimension E2 is equal to 2, and minus 1 has one eigenvector, dimension E3 is equal to 1. Then what is sum of all dimensions of eigenspaces? Dimension E1 plus dimension E2 plus dimension E3 is equal to 2 plus 2 plus 1. That is equal to 5, which is equal to order of A. Hence, A is diagonalizable. Look at this example. If A is a 3 by 3 matrix with two eigenvalues, with each eigenspace with dimension 1 is A diagonalizable. So here suppose A is a matrix of order 3 by 3. How many eigenvalues are there? Number of eigenvalues is equal to 2. Number of eigenvalues it is given, it is a 2 is equal to 2. Then let us suppose that they are lambda 1 and lambda 2. And then eigenspaces, how many will have? Each eigenvalue will have an eigenspace. For lambda 1 E1 is eigenspace, for lambda 2 E2 is eigenspace. And it is given that with each eigenspace dimension 1. So dimension E1 is equal to 1 and dimension E2 is also equal to 1. Then what is the sum? What is the question asked? Is they diagonalizable? So for diagonalizability, the sum of these two dimensions of eigenspaces must be equal to the order of the matrix. So dimension E1 plus dimension E2 is equal to 1 plus 1 is equal to 2. It is not equal to 3. It is not equal to the order of the matrix. That is why A is not diagonalizable. Now the second example on the same concept. A is a 5 by 5 matrix with two eigenvalues. One eigenspace is three-dimensional. What could be the dimension of the other eigenspace if A has to be diagonalizable? So what are all given in this? A is a matrix of order 5 by 5, and then there are two eigenvalues lambda 1, lambda 2. Then eigenspaces will be E1, E2, and it is given that dimension E1 is equal to 3. Then what is the question asked? If A to be diagonalizable, what must be dimension E2? So A should be diagonalizable implies a dimension E1 plus dimension E2 is equal to 5. That is order of A. So 3 plus dimension E2 is equal to 5. Therefore, dimension E2 must be equal to 2. Another example. A is a 4 by 4 matrix with the three eigenvalues. One eigenspace is one dimensional. One of the other eigenspaces is two-dimensional. Is it possible that A is not diagonalizable? So here you are given a matrix with 4 by 4 order. So and it is given three eigenvalues. So lambda 1, lambda 2 and lambda 3. Lambda 1, lambda 2 and lambda 3. Then three eigenspaces E1, E2 and E3. Now it is given one eigenspace is one dimensional, so dimension E1 is equal to 1, and one of the other, that means remaining two eigenspaces E2, E3, among them one is dimension E2 is two dimensional, so dimension E2 is 2. Then what is remaining? E3 is remaining. Then we will say that dimension E3 must be 1 because there should be minimum one eigenvector for each eigenvalue. When eigenvalue is there means minimum one eigenvector should be there. So that means the third eigenvector lambda 3 must be having one eigenvector. So dimension E3 must be minimum 1. Then sum of all these three dimensions is equal to 1 plus 2 plus 1 is equal to 4. That means which is equal to order of the matrix, hence A must be diagonalizable.